Thank you, everyone. I hope everybody had a nice lunch and enjoying the weather out here. So today, myself, Paras, along with my colleague Anmol, will be emphasizing on a topic which is sort of a problem or a bottleneck that we might have encountered when we started our AI/ML journey. I can take a stab on it, like maybe long time back when I started. Jupyter Notebook was my first getting started guide. So probably a raise of hand if that was the case with anyone else, like Hello World or something that we did with the Jupyter Notebook. That's great. So something on those lines is what we are trying to enforce, and that's the journey of AI data model that whether we are engineer, data scientists, that we've been trying to figure out. So it works fine when we get started, but slowly when we move out to the production, that's where we get stuck. So this is the basically the problem statement we are emphasizing from hours to milliseconds, scaling inferences with serverless on Kubernetes. As I mentioned, Anmol and I, Paras, will be covering this talk. But before we get started, this is a disclaimer that the content and the views here are completely our personal views and are not representing the organizations or the company institution that we are employed with. So giving or setting up that as a context. The agenda is that we'll be getting started with why many of the AI projects fail. What is the bottleneck that we don't see while we are getting started, but eventually that's the thing that is bound to happen, followed by the inference trilemma. This is something, I'll say, an interesting section. We'll keep it as it is for a while, and then eventually how you can get started with choosing a solution, followed by a demo. And a demo is incomplete without any metrics and any benchmarks. So that's what we are going to cover as part of that benchmark comparison. Then there will be some suggestions of what are the potential optimizations that each of us can try to incorporate, and what are the key takeaways that we can take. That's what basically the intent. We want some key takeaways, some learning, some insights. We want to share our learnings. We want to learn what you've tried out, what your experiences has been, and help build the open source community, followed by some quick references. So this is where I was getting headed to. So where many AI projects fail, or how do we begin? So when we get started, or at least I can take an example long back, or at least 5-6 years ago, my first projects that I was doing on AI/ML getting started was a sentiment analysis on a Python script. And what I did was wrote something on the Jupyter notebooks. I vaguely remember writing something down in the different cells. And then I used to pass a string, and it used to say whether it's a positive and negative. And then I integrated with a messaging queue product and saying that if it's a positive, then pass on the message. But if it's a negative, then give a warning back to a user that you are sending something which does not carry a positive intent, and maybe something you might want to revisit and course correct. But that was something from my novice point of view that I could do pretty nicely, pretty quickly from a POC perspective. But back then, or even now, many of the folks who are starting now never thought about what are we thinking about scaling it out loud. Like, how do we want to scale it out to a production or to a wider audience? Like, it's fine if I'm presenting this POC to a small team or to my managers or to a small bunch of people, or maybe some hackathons. But where do we eventually say it going out to the audience? So this is where eventually, like many of the cases, things fail. Things works on my machine, things works on my my friends' machines, but they are bound to fail on a production, or you can say unless some things that we have not thought about. And when we try to run it out, these are some challenges that we face. The challenges are like the horrible cold start problem. If you are running in a VM, for example, the snippets that I've shared here, this is just a piece of a demo where I ran a simple text, I love this service, and it is absolutely wonderful. And you can see it took almost 140 milliseconds as is for the processing time. That was for one curl request for one user being served by a single VM. So what are the challenges, or you can see the issue it encountered was, number one, it was horrible cold start. The first time we make a query, it took additional time it is going to take additional time for every user who does that, because of there's no there hasn't the model, all the inferences has not been loaded. So it takes additional time. The follow-up request will be faster. It will be much quicker, but the first one is going to take the time. And by the time, if we are expecting multiple concurrent requests, since we are not supporting the concurrency, other requests are going to pile up. So it's not just that the first request it's piling up. The first request is setting the tone for the follow-up or the concurrent requests that are expected to come. And since we are talking about traditional compute instances or VMs, like I took the example of running Jupyter Notebook in my local server, we are not talking about manual and slow scaling. We have not thought about how we can scale it up, and it being costly, inefficient is another major factor. Like, if I have a VM running this, however, I'm not expecting this VM is to be used 24/7. So what's going to happen is I'm bound to pay for the price for this infrastructure for the time even when it's not being fully utilized. And in the AI ML, I guess we've heard a lot. All these machines are compute intensive, and they come with heavy cost. So if you're not utilizing the 100% of the machine and not making consistent requests, then we are expecting a decent bill in the monthly or the yearly cycle of our cloud infrastructure. So that's what we want to avoid. And the last one, but not the least, is there's no concept of auto healing. If, let's say, if I'm running this as a Python server in my machine, that goes down unless, like, by default, out of the box, there is no way that it can be smartly handled unless there is some smart way of integrating with some third parties that we're not talking about. But these are some of the initial few bits that we can quickly see as the core problem. There are many other factors, like how do we handle with overfitting, underfitting, data quality, the poor processes, lack of CI/CD pipelines, and many other factors being in. One more thing I would like to say is, in this talk, when we are saying about hours from hours to milliseconds, we don't want you to think from a perspective that it's only about hours to milliseconds from the latency perspective of AI ML workload. We also want you to take step outside of that latency perspective and think of the persona where how much time it takes for a developer to move their code from development environment to a production. How much time it takes for you to build that infrastructure. Because when we talk about a VM, there comes many other things. It's just not that we just set up a VM standalone. There comes many internal things around that. When we talk about developer workflow, it's not just that we build a VM and we launch. There comes many other intricacies around that. So there are hours of wasted resource, hours of wasted engineer efforts, hours of design discussions that happens, and all of this plays as critical role as the latency plays. So with that, this is where the inference trilemma comes in. So I'm just going to give you what the inference trilemma is. That in our computer or algorithm, or you can say building design systems, all of us would have heard about CAP theorem. So think this as this way, as a CAP theorem, but instead of CAP theorem, we have low latency, cost efficiency, and high agility. Now, what are these factors? What we can do to address this, and what could be a way forward to ensure that we build a solution, we design a solution, we propose a solution that kinds of addresses the problems that we are encountering, or at least we can better address. So with that, I'll let my friend take you through the inference trilemma, and he can provide you what other issues we can avoid.
Sure. Thanks, Paras, for setting the context. Okay, so from inference perspective, if we are talking about not just inference, but other ML AI training related activities as well, low latency, cost efficiency, and high agility are some of the key concerns that one should be focused on. just start thinking about a problem statement wherein you have put your model in production and you want to serve it. Now, as and when there will be a burst in the number of user requests, you would want to really have the capacity scaled for your model, right? The servers that are there. In order to scale the capacity, you would go ahead and probably try out using some auto scaling group or putting some horizontal pod autoscaler, etc. Instead of thinking whether there can be any tweaks performed the way model is getting served itself, whether any logical, let's say, implementation can be done at the model serving layer itself. We rather think of scaling platform and infrastructure, and then we go about getting into a vicious circle wherein if at all we are scaling the stuff, the new stuff that is coming up, the new replicas that are coming up will be going through a warm-up cycle. So they will first have the cold start issue, then they will be getting warmed up, and then they will start serving. And when you have enough replicas to serve your case, then in that case, your cost will go up. So basically, you started from a position wherein you had only a handful of requests. Those requests grew in number. Now, in order to serve those numbers that you actually have in terms of requests, you scaled up your platform. When you scaled the platform, you hit the cold start issue, then the platform warmed up. By the time you are actually serving the request, your cost has already bursted up. So we have covered low latency and cost efficiency as two of the areas which are certainly getting influenced. What about high agility? So when we talk about scaling the infrastructure based on our requirements, we generally have to bake in some sort of DevOps tool chain as part of our AI ML workload serving. And this is where, if at all we are working with a platform like Kubernetes or we are working on some traditional VMs, baking in those auto scaling criteria actually require you to write a lot of manifest files and coordination with a lot of tools. Like you could be using something like Tilt or Scaffold for doing some local, let's say, testing for your microservices or the serving platform. Then you could be going ahead and having a proper MLOps kind of setup done in order to have your workloads served. So this is where the thing is that there are trade-offs in these three areas, and two of them can be achieved at once in, I would say, a trade-off wherein the third one you have to compromise. So that's the inference trilemma. We specifically can take this particular example as to what I explained. Let's say you have one replica which is currently serving, the number of requests went up. Then you have 10 replicas which you need to scale to. You go ahead with having horizontal pod autoscaler applied. Once the horizontal pod autoscaler has applied, the horizontal pod autoscaler itself, based on the schedule that it has been tuned to work on, and also based on the scheduler that you are working with, based on the autoscaler that you are working with, the time will vary as to by when the new workloads or the new replicas will be coming. And overall, just to scale up the things, you have got to a place wherein you have to go with some complex deployment scripts and some tool chain. So this is where we come to an analysis of first, as a first layer, which particular platform to use for your serving requirements, whether you should be going with traditional VMs, whether you should be going with Kubernetes platform, whether you should be going with something like a serverless compute, or whether you should be building your own stack. If you talk about traditional VMs, certainly you have full control over the operating system. Likewise, you have full control over operating system along with container images when you come to Kubernetes, because certainly you can have node level operating system tweaks and container level operating system and the library related tweaks. But when we come to serverless, you have to worry less about the underlying platform, but whichever serverless provider you are choosing, you need to make sure that your workloads are tuned to work on that particular serverless provider. So it's not that there is some one size fits all solution kind of answer to this particular problem. So first level of comparison is that the platforms that are there, they have some benefits to offer on their own. And when we compare these platforms against each other, there are some trade-offs. There are even some capabilities wherein you can actually have serverless workloads run via Kubernetes. So that is where the Kubernetes infrastructure itself will need to be managed by you. So that actually has the management toil added to it. The other thing is from compute instance perspective, we have legacy applications and static workloads generally preferred for running on VMs. But if we are talking about traditional applications, still it makes sense. If we are already going with applications which have to suit the modern ecosystems, then in order for them to be run on VMs, you will need to have some auto scaling groups, you will need to have some auto healing properties, like you would be using something like supervisor D or something for making sure that the instance keeps up, the process keeps up, even if there are any issues happening, or if, let's say, there is an exit, then it is able to recover from that. When we come to Kubernetes, it is actually offering us with all these properties, liveness probe, readiness probe, etc. So we don't really need to worry much about it, but to make sure that the application has the right signal handlers implemented. So it actually becomes a portable solution, because you are not really vendor logged in unless you are using some specific annotations, etc. for the provider or the underlying hardware. And then when it comes to serverless, it is more or less offering the capabilities of Kubernetes, but some of the key features are that Kubernetes natively doesn't have scale down to 0. So what if during your off-peak hours you really don't require your infrastructure, you want to have FinOps aspects also to be taken care of? This is where serverless could be an option, but there are equivalent options available in Kubernetes if you use something like Knative or KDA, right? So this is where it's a trade-off of management complexity versus ease of deployment. So you need to see whether you want to aim for high agility, wherein developers are the main runners who are driving your ecosystem, or you have a dedicated platform engineering, site reliability engineering, or DevOps team, which can take care of horizontal tools for you, and you can provide abstractions to the developers, so they just can opt for those kind of abstracted services from the platform. And this is, I would say, a comprehensive view of how things look like at a high level. So I'll just highlight a couple of things. We will be focusing on scalability aspects from a discussion perspective. This is where, as I have mentioned, scale down to 0 with Kubernetes is also possible. Now, for people who are here in this conference would have already gone through some of the sessions, and even the next session is focused on VLLM and Kserve. So I'll just give you a glimpse of how things would be relating. So scale to 0 is something, as I mentioned, can be achieved by using KDA or Knative. Even if you are using regular Kubernetes, then you can go ahead and have your scale to 0 done by using the kubectl scale deployment related operation, but it cannot be done in an automated fashion by using HPA. Why you would choose between Kserve or Knative or KDA is that, like, Knative is highly focused on HTTP request-based metrics to perform the scaling, wherein if you want to have custom metric-based scaling, you would be going with KDA. So KDA and Knative are complementary, I would say, when serving the ML workloads. And likewise, if we are talking about something like Kserve, that's generally for actual serving of the ML workloads. It actually gives you things like going ahead with having proper model mesh, having more granular control over routing of the models, etc. So this is where there are aspects which can be realized in different platforms, but then you need more work to be done in order for them to be realized. So performance, as we know, low latency performance can be achieved in Kubernetes and serverless, as well as VM workload-based deployment models. But the only thing is that there are a lot of traditional design-related issues that you have to solve in VMs in contrast to Kubernetes and serverless. From scalability perspective, I have already explained and given you a glimpse of what it looks like. From serverless perspective and scalability and scale down to 0, it's something which is a native feature for most of the managed platforms. If you are using one on bare metal, then you have to design for the same. And when it comes to cost, cost is pay per use or pay as you go sort of when it comes to serverless. But then if you really are an advanced Kubernetes user, then you might be getting more control in Kubernetes based deployment only. So that's where you might want to go with performing a proper benchmarking of how things look like in serverless versus how things look like in Kubernetes. Ultimately, it gives you more control because you can have hardware level segregation, etc. exercised as per your requirements, and even security isolation is something that you can achieve in a better manner in Kubernetes driven design. And from overhead perspective, I think whatever I have discussed so far actually has pointed out to things which could be there from overhead perspective. So that was on the platform layer. We also need to focus on other things, though this particular talk is going to focus more on the platform side of things, but there are some of the other things that you should focus on, especially when you are working with Kubernetes and serving the models. One is you certainly can have model images just because you have CUDA drivers, device plugins and whatnot. reaching tens of GBs very easily. So one approach is that you go with a multi-stage Docker build approach. Let's say if you are using a Docker-based container image building technique. In that case, you can have the libraries installed, and then the exports of those, the runnables that are there, you can actually transfer to the other layer. So this is where like using a multi-stage Docker build actually gives you some understanding. There are other projects like Docker Dive, Scout, etc., which can give you a layer by layer understanding of how your container image looks like. So that's where feel free to explore that particular area. The other thing is there is certainly a need for having images prefetched because if you just have a container just getting up and it has 10 GB worth size to download, you could be having contention at the network layer, you could have some issues at the node layer, a lot of issues could happen, and you could be delayed in just starting up your container itself. By that time, it could be that your spike has also gone away. So this is where prefetching of images is something which earlier was not possible in many platforms. People used to go to their etc local files and all, and they used to write some code wherein they could do the fetching while they are booting up the nodes. But these days there are streaming image container pulls that are available, which are available in a lot of platforms. So that's another area at a high level which you should be focusing on. The other thing is there is a debate as to whether we should go with FinOps optimization or whether we should go with some warmed up stuff, because there is always a trade-off, as I mentioned, between the cost and the latency thing. So that's where keeping a min scale value of 1 is something which is not going to harm you, but certainly it's something for you to decide, and depending on which kind of workloads you are serving, things will vary. So I'll pause here. I'll give it to Paras for taking some demonstrations. After the demonstrations, we have some specific deep dive areas wherein we will focus on not just the platform things, but what exactly you can do from scaling up your inference in even a native ML AI manner. Yeah.
Thank you, Anmol. So we talked quite a lot for past few minutes. So I thought how we could get our hands dirty. So instead of we sort of knew that we won't be able to have sufficient time. So I've got a pre-recorded demo, but before that, here is a GitHub repo link that we have where this code is available that we have used for the demo. And should we go through the code, or okay, maybe we'll just quickly hop onto the video. So here we could see I have a serverless, it's a managed service called Cloud Run. And then here I have a traditional VM followed by a Kubernetes cluster. And so here in the Cloud Run, I have a CPU and a GPU, and we'll come back onto why this comparison helps us a lot. And this is the benchmark that I'm executing. So 60 seconds, 400 users, it's what it kinds of simulates to for all the 4 platforms that we have out there. So we will be loading the server in our VM, the Python server in one of our VM. So just SSHing into that. Once I've logged in, the traditional Python server is the application basically that serves the request that we are then going to simulate to, or that the user will be firing to. Basically the 60 seconds and 400 users that we just saw in the previous screen. So this is going to run an application. So here we are using Flask API. So it's now ready and serving the request at port 5000. These are the external IPs for all the 4 platforms: VM, Kubernetes, serverless CPU URL, serverless GPU URL. So these are the URLs where the request will be fired on. So we are using K6 to help us summarize the benchmarking that we are doing. So this is going to run all the 4 simulations in parallel. And yeah, I think it should be pretty much done. And wait. With that, I think, so now it's going to simulate the queries that we just went initially. So we'll just quickly cross-check if we are getting as expected response. So we're getting 200 HTTPS response in the VM. We'll check the same for our Cloud Run service. So the logs the logs are returning 200, and the same is the case with the GPU. So this to ensure that these are actually serving the request, the the applications that we have deployed, the workloads we have deployed in the appropriate infras are actually deploying. So now we are going to check for the Kubernetes, and here we are going to first check the logs of our nodes, the cluster, to see things are running as expected. So that kind of justifies that while the workloads are running fine, all of them are working. But one more thing on to add is when we go on to the workload section, it'll be the next frame. Yes, so it says does not have minimum availability. That's possibly because the huge load that we are testing it through. However, it is still going to show us the 200 response because it's still being able to cater to the request, but the minimum availability that it was expecting, it's kind of taking a thrust on. So with that, we could see that all the 4 infrastructures that we have deployed is successfully serving the request. We are getting all the response generated as we were looking for. And now we basically would be generating the graphs because that's what we want to. So with that in mind, this I think should be pretty much done in terms of the, so post that, yeah, we'll just run the Python 3 to help us plot the benchmarks. And in the next slides is where basically the magic will be. So before we go into the graph, this is just a quick explanation of what we want us to expect from the simulations we did. So we are doing a load test for 400 concurrent users. So in the demo, it was for 60 seconds. The 2 metrics that we are evaluating on is the average latency and the throughput. So the lower latency, the better it is, and the higher throughput, better it is. So with that, here we can see whatever we have just talked about with a bare minimum change in the infrastructure without delving deeper into the application aspect. This is the huge improvement in the latency and the throughput that we could see. So I'll not go into the exact numbers, but I guess it'll be visible to everyone that the latency from VM to GK and then from, so basically from virtual machine to Kubernetes and from Kubernetes to serverless talks about it itself. So this is a comparison of the latency and the throughput, but I guess this should also raise a question in everyone's mind. Why do we only see a minor difference between a serverless CPU and a serverless GPU? Although we talked about a lot, but there is still a very slight difference. And the answer for it is the type of workload we are running in. The workload that we have run is not ready to use the GPU at its best. It's basically a serial sequentially computing or like basically not a workload that could emphasize on the parallel computing. So that's why irrespective of whether you use a CPU and GPU, you don't see a huge drastic improvement. So when we are planning to move from CPU to GPUs, a key aspect to also notice is what kind of a workload that you are running on. So we also wanted to bring that aspect of it in this chart, in this talk, and hence the comparison. But I guess that will help us to make a point of it. With that, we'll quickly go through the key takeaways.
Yep, sure. Thanks, Paras. Okay, first thing to understand is that the VM-related demo that we saw was based on a WSGI server, web server gateway interface that was supporting synchronous requests. What we changed slightly along with the platform was that we changed the application to Fast API instead of being on Flask, and we changed it to ASGI instead of WSGI. So it was asynchronous web server gateway interface that we were leveraging. That actually helped us perform asynchronous operations, and hence we were able to have more performance, just not from a platform perspective, but also from application perspective introduced. Other thing is, as I mentioned, DevOps toolchain is something that is really very critical. You could be having n number of CI/CD things, etc., but then unless you have a proper sorted out process for how to have promotion done for your workload related developments from your local to any of the higher environments, and then providing a feedback from higher to your ecosystem so that you can have a continuous feedback loop, you won't really be able to achieve maturity. Other thing is quantization is pretty normal these days. It's also being offered by platforms. You could have seen Triton, TensorRT and whatnot. Some hardware level optimizations also could be getting performed. So for people who don't really understand quantization, it is about having the numerical precision reduced for the weights and activations. Also, there are model-related prunings that are available, which you can do for the weights again, in order to reduce the size of the bit integers that are there. Like if we are following quantization, and that too is a post-training quantization, that means you are having the training, etc. done, and then ultimately the bit integer space you are translating from 32 to, let's say, 8 or 16, so that you can effectively serve your workloads. This really has some hit on the accuracy, but then it's a trade-off again that you are making, whether to go with accuracy or whether to go with the faster inference. Then from scalability perspective, we have showed you how the platforms contrast, but ultimately it will be very much dependent on your workload and the type of application that you are running on. Compiled models generally are better suited. These days there are interoperable common standards like ONNX available. So Open Neural Network Exchange is the full form for ONNX. It actually performs pretty well if you have to turn from, let's say, PyTorch or Keras to a common standard which can be served effectively. You can combine that with things like TVM, wherein you would be having more of hardware specific compilation done. So you can have your workloads from a serving perspective focused on CPU, focused on GPU, etc., depending on which kind of workloads they are. So using ONNX along with TVM or even other optimizers, etc., are available. Like Intel has something called OpenVINO. There is NVIDIA RT as well, and Triton related things that I mentioned. All those things can be leveraged. Batch inferencing is something which again comes as part of a lot of platforms. Dynamic batching is also available in serving platforms like Triton. You actually have hardware optimization yielded because of batching. You actually have a lot of inference related operations collaborated or contained in one operation itself, a single operation. You certainly have a shared memory there, but then the way the tensor level optimizations work, this is where you actually can perform validations as well at the input or the output before the tensor level operations are converted back to the requests, the responses for the requests that are there. So these 2 points are very important. Along with quantization, you need to focus on some of the application level stuff. Then these are some of the points. When we talk about accelerated GPUs and TPUs, I think this is pretty normal these days. People think that GPUs and TPUs could be adding more to their applications from cost perspective and performance perspective both. It's not always true. Sometimes CPUs could be better suited. That's what was shown in the example which Paras demonstrated, wherein even if we had the same application run on GPU, it was just performing almost reasonably equivalent to the CPU one. Then parallelism and concurrency is something that we need to benchmark against. These are like some standard takeaways that you should understand. Caching and memoization is also something which can be implemented at various layers. You can have the output level caching done or the model level responses cached, but there are platform optimizers and compilers that actually can have the intermediate results also cached. So you need to focus on caching not just from end user perspective. The intermediate state is also something that can be cached and which can add really good value from inference perspective. And I think with this almost we are at time as well. There is a network topology that Paras will cover for 1 minute, and then we'll conclude this talk. Yeah.
So we started this talk saying that what were the issues that someone faced when we started AI or ML project in their local machine. We know what were the challenges, and eventually moving it to production, we had to scale, and we thought of how about moving it to cloud or maybe to serverless platform. And that's where we had this talk. So considering this slide or this session as you can say, we are just stepping out one dimension above it to think of how to avoid doing the same mistake when moving to cloud or to a serverless. So basically what we are trying to do is, when we are moving to AI ML or trying to run something, what we want is more and more compute. But if we go to a cloud lock-in, or if let's say we start with a managed service to a specific cloud, or let's say we go with a app first strategy, then the chances of getting a similar bottleneck could be higher. And that's what we want to avoid. So one thing that could be tried out is, we could start with the network first strategy, where think of a way irrespective of how or where our production may scale to, but we should have our networking topology built in a way where we could actually integrate multiple cloud providers, and we could leverage the best out of among all of them. Like whether we want one GPU, one TPU, one CPU, the network should be good enough that it can actually interact across multiple clouds. It can interact across multiple services, be it managed or open source, or across multiple services, because once we have an app ready, which is tightly coupled to a particular ecosystem, doing the reverse engineering of it will not be impossible, but it will be tricky. So it's going to take a bit more time. So to avoid that, this is a very high level diagram that we have just tried to put out our thought to have a representation where we can build an architecture, a topology where your multiple clouds, multiple services can interact with each other, and then we can create any complicated design or services we want, irrespective of what compute we are looking for. So that's a additional takeaway that I would like us to take us from this talk. And here are some pointers, maybe some ready to use Terraform modules that we could try it out. So it's on to us that which or architecture you want. So we've got a couple of steps, whether you want to set up the hybrid cloud or Kubernetes or serverless instances, or you want to integrate with some other cloud provider. But that's mostly as a side note. So that's mostly we had, but we'll hand it over to Anmol in case we want to add anything else.
Yeah, sure. Thanks all for being patient listeners. We are up for questions, but we are also approaching the time. I think the next session is already scheduled, so should be starting. Kindly pardon for the delays. We are here at the hall only. If you have any questions, we can meet outside. Thanks, everyone.